Welcome to This Explainer. We're all taught in school that force equals mass times acceleration. It's totally ingrained in our brains. But here's a wild thought. If engineers relied on that exact equation to land a multi-million-dollar spacecraft like Chandrayaan-3 on the lunar surface, their calculations would be completely wrong, and the rocket would literally crash.
So why exactly does F equals ma fail to calculate the launch force of a rocket? Well, to solve this high-stakes mystery and understand why Newton's famous formula isn't the whole truth, we first need to take a step back. We have to peel away the layers of what we learned in high school and look at a foundational concept in physics. Because the answer to why a rocket breaks this rule lies in a hidden assumption that we make every single day. Let's dive right into this.
Okay, so it all starts with momentum. You can basically think of momentum as a measurement of the sheer amount of motion that an object has. Mathematically, it's really simple. It's just the mass of the object multiplied by its velocity. But conceptually, you can think of it as a vector that measures just how dangerous a moving body is. It possesses both a magnitude, a concrete value, and a direction that perfectly matches the object's velocity. Picture this. Compare a heavy coconut falling from a tree to a tiny bullet fired from a gun. Which one of those is more dangerous? Well, momentum captures exactly why both possess an incredible amount of motion. See, the coconut has a high mass but relatively low velocity, while the bullet has incredibly low mass but extremely high velocity. Because momentum is mass times velocity, both of these objects can carry a massive and equally dangerous amount of momentum. Section 1. The real second law. Now that we've got a solid grasp on momentum, let's uncover what Sir Isaac Newton actually stated. Newton's true second law says that force dictates exactly how fast an object's momentum changes. It explicitly states that the rate of change of momentum of a body is directly proportional to the applied force, and this change happens in the exact direction the force is applied. Notice anything missing? There is absolutely no mention of mass times acceleration in this original definition. It is entirely about momentum. Next up, pushing the broken car. Let's visualize how force, time, and momentum interact in the real world with a super easy, relatable example. Imagine you're pushing a broken-down 1,000-kilogram car along the road. You start at rest, meaning your initial momentum is exactly 0. But you dig in and push for 10 straight seconds. Eventually, the car reaches a speed of 2 meters per second. Multiply that by the car's 1,000-kilogram weight, and our final momentum is 2,000.
Remember, Newton said force is the rate of change of momentum. So we take that final change, 2,000 minus 0, and divide it by the 10 seconds it took. We find the rate of change is 200 kilogram meters per second squared. And scientists luckily define this exact metric as our standard unit of applied force. We call it 200 newtons.
This brilliantly illustrates the law's proportionality in action. If you call a friend over and 2 people push the car, you're doubling the applied force. Because it's directly proportional, the rate of change of momentum also doubles in that same 10 seconds, meaning the car goes twice as fast. If you get tired and apply half the force, the speed gained is halved. And, naturally, if you push the car east, the change in momentum happens toward the east. It's wonderfully intuitive when you really think about it.
Section 3. The mathematical proof.
So how do we actually get to that F equals ma equation we're all taught? Well, it builds using some pretty elegant calculus. For incredibly small time intervals, as time approaches 0, force equals the derivative of momentum with respect to time, or F equals dp over dt. In step 2, we know momentum is just mass times velocity, so we substitute that in to get F equals the derivative of mass times velocity. Now in step 3, if we assume the mass of the object doesn't change, we can pull that constant mass m outside of the derivative. That leaves us with mass multiplied by the derivative of velocity over time, and since the rate of change of velocity is acceleration, boom, we arrive smoothly at step 4, force equals mass times acceleration. But wait, the absolutely crucial point is right there in step 3. We could only pull mass out of the derivative by making a huge assumption, that the mass of the object never ever changes. To use F equals ma, the mass of your body must be perfectly constant, just like our broken down car. Moving on to solving the rocket mystery. And this brings us completely full circle back to the Chandrayaan-3 mission. You see, rockets literally break the rules. During a launch, a rocket isn't like a car rolling down the street. It's a massive machine rapidly burning huge amounts of fuel every single second. As that fuel burns and exhausts out the back, the total mass of the rocket is continuously decreasing. The mass is absolutely not constant. Because of this, that core assumption required to use F equals ma is completely shattered.
If you use F equals ma to calculate the force for rocket launch, your math is fundamentally flawed, and you are not making it to the moon. Therefore, for calculations involving changing mass, space engineers must rely on Newton's actual original law to get the correct trajectory and land successfully. They have to use the equation force equals the rate of change of momentum, or F equals dp over dt. This original calculus-based equation is universally valid because it doesn't wrongly assume a constant mass. It simply looks at the total changing momentum of the system.
Our final section, the equation in action.
To really cement our understanding, let's look at one final practical mathematical application. Imagine we have an object with a constant mass, m, and its displacement over time is given by the equation x equals 10t squared. How do we find the force? Well, first we need velocity, which is simply the rate of change of displacement. We take the derivative of 10t squared, which gives us a velocity of 20t. Since we know mass is constant here, we can use force equals mass times the rate of change of velocity. We take the derivative of our velocity, 20t, which just leaves us with an acceleration of 20. Multiplying that by our constant mass m, we find our final applied force is a clean 20m.
Now that you've unlocked Newton's true second law, I want to leave you with a quick momentum challenge to really test your intuition on everything we've just covered. Imagine two balls. One is 1 kilogram, the other is 2 kilograms. You apply the exact same identical force to each for the exact same amount of time. Which ball gains more velocity? And critically, based on the actual math, which ball will have more momentum at the end? Take a moment to really think through the physics. The answer might just surprise you.